Welcome back to Algorithms and Uncertainty. Today we will be again talking about the online Steiner tree problem, for which we've already seen an O of log k competitive algorithm, and we've also seen that this was more or less the best possible, namely that you could get no algorithm which was better than omega of log k competitive, where k was the number of terminals in our sequence. But whenever you see such results, you should be aware that this competitive analysis is actually taking a very pessimistic view because it is an all worst case analysis. So what's the problem? Well, in advance we don't know anything, and also what happens over time is somehow taking a, Murphy's Law perspective. What can go wrong will go wrong. And therefore today we will be turning our attention to probabilistic models for the online Steiner tree problem. We've already seen in the context of optimal stopping that probabilistic models allowed us to derive much more meaningful results than what we could have done via worst case analysis there, because worst case analysis in the case of optimal stopping was entirely pointless. This was not exactly this way in the Steiner tree problem, but also today we will see that if we assume to have some prior knowledge, if we assume that the input is drawn from known probability distribution, then we will be actually able to derive a better result, namely something like a competitive ratio, but which will then be constant. At the same time, recall that in optimal stopping it was also enough if just the input arrived in random order. This will turn out to be not enough in the case of the online Steiner tree problem, and still there we can derive that the competitive ratios will not be better than some constant factor times log k. But before getting there, let's quickly recap the definitions. So what's the Steiner tree problem? Generally, we have a graph consisting of vertices and edges, and we have edge weights, which are non-negative for all edges. And then we'll have to have terminals. Again, here we are taking the perspective of a rooted Steiner tree problem. So we have one root vertex, which is just known in advance, and then a sequence of terminals T1 through Tk is revealed to us over time. And now we'll have to maintain a subset of the edges, such that the set of all terminals which have been revealed so far, all of these terminals are connected to the root, and this way also to each other, because this is an undirected problem. So this has to be connected using only the edges in S and not the other edges, of course. Good. What's our objective? Our objective is simply to minimize the sum of the edge weights of the edges that we select. And for this, we derive this log k or O of log k competitive algorithm. So the cost that our algorithm incurs is at most O of log k times the cost of an optimal offline solution. So in this optimal offline solution, we assume to have not only perfect knowledge of the input instance, so to know all these terminals beforehand, but also that we have unlimited computational power, because this is actually an NP-hard problem. So in polynomial time, assuming that p is not equal to np, you could not even compute this optimal offline solution within polynomial time, even if you knew all the terminals. Good. And for this we had now some simplifications for this problem. Namely, what could we assume? We could assume that without loss of generality, the graph is a complete graph and that the edge weights fulfill the triangle inequality. Why could we assume that? Well, we could assume this because instead of taking a direct edge, we might also take a shortest path. And whenever we are adding, instead of one edge, we're adding a shortest path between two vertices, this will have the same effect on the Steiner tree, namely connecting things. And so this will only make things better for us if instead of taking an edge, we take a path of this particular length. So this is why this is all without loss of generality. And given this, we can now simplify the problem, or we can see the parallels to the spanning tree problem. Recall that in the spanning tree problem, usually you would want to choose edges so that all vertices of your graph are connected. Now you can also consider this the same problem where only a subset of the vertices have to be connected. And this is also well defined if your graph is a complete graph. And what you now see is that this would also be a feasible solution to the optimal Steiner tree problem. Namely, here in this first case, you're only connecting the root and the terminals to each other. So we restrict the graph to only have the root and the terminals. And now you see, okay, how can I connect these vertices together only via the direct edges between them? In the Steiner tree problem, you may also take intermediate vertices, which are not terminals or the root, to make these connections, and sometimes this will give you cheaper solutions. But these solutions will only differ by a factor of 2, namely the optimal Steiner tree solution will never be more expansive than the minimum spanning tree of this graph where you're restricting to only the root and the terminals, but also this minimum spanning tree will be no more expansive than 2 times the cost of the optimal Steiner tree. Good. This is all recapping what we've seen so far. What we'll do now is we'll introduce a very simple probabilistic model, and for this, then what's the point of this model? We assume to have some prior knowledge about what will be happening, and then we will design a very simple algorithm and then show that for this we can actually get something like a constant competitive ratio, and our proofs will go via exactly these tools. Our first approach for the Steiner tree problem in a more probabilistic sense is now to assume that in advance we know probability distributions the terminals are drawn from. This is also an approach that we've seen for optimal stopping, and what we'll do now is simply to say, well, in each step we get a terminal which is drawn from one probability distribution. This probability distribution might be different in different steps, and we do know in advance these probability distributions. So what will this look like? We'll have now t1 through tk. Those will be random variables. And each ti is drawn from a known distribution. So we'll have the probability that ti takes the value v. We can simply write as p subscript v superscript I. So this is the probability that we see v as the terminal in the ith step. And we also assume that t1 through tk are independent. So importantly, these distributions might not be identical because we might have a different probability for each step I, but importantly these are independent, so what we see as the outcome in the first step is independent of what we see in the second step, and so on. You could in principle model this as a Markov decision process. How would you do this? You would now have to keep track of, in the state space, which terminals you saw so far, which edges you chose, and in the action space would be adding further edges to your set, to your Steiner tree. But it won't be surprising that now this state space and this action space will be enormous. They will be exponential in the number of edges and number of vertices. Why isn't this surprising? Well, a special case of this problem would be that for each I, only exactly one of these PIV is 1 and the others are 0. Then we see just a fixed sequence of T1 through Tk, which is known to us beforehand. So then solving this problem or computing the optimal policy would be nothing but solving the Steiner tree problem for this problem, which we know is NP-hard. So generally computing an optimal policy for this problem turns out to be NP-hard. What you could do now is you could try to approximate the optimal policy. And this is indeed an approach that we'll be taking in the next lectures, but today we'll do something stronger. We'll be designing a simple algorithm and we'll compare its performance to the optimal offline solution. And because we are able to do this comparison, we are automatically also approximating the optimal policy, because the optimal policy just cannot be better than the optimal offline solution. Recall that the optimal offline solution that we will be comparing ourselves today to actually knows this sequence of T1 through Tk beforehand. So what does our algorithm look like? Our algorithm is actually pretty simple. For the online Steiner tree problem, we used the greedy algorithm. We just connected a newly arriving terminal to the existing terminals the cheapest possible way. Now we'll do something very similar, but how do we make use of the fact that we know these probability distributions? Well, we'll have now two stages. In the first stage, we'll just draw from each of these probability distributions once. We'll compute a Steiner tree on this. And then afterwards, we connect the actual arriving terminals to what we've computed in this first stage, which was actually only making use of the fact that we know these probability distributions. So the algorithm is called greedy with sample. And the first thing that we'll do is we'll draw T1 prime through Tk prime from the known distributions. And we'll let T prime be just the set of these. And we'll initialize S as a minimum spanning tree on these T prime terminals. Note that those aren't the actual input. Those are just some terminals that we draw from our known distributions to initialize a set S. But then, only then, the actual terminals will arrive. So when now Ti arrives, meaning it gets revealed, what do? We now let V be the closest of R T1 prime through Tk prime and T1 through Ti minus 1 to Ti. So we'll now see all of these we connected so far. So R T1 prime through Tk prime, they were already connected here. And of course also the other terminals we connected so far. And now something important can happen, namely if V is equal to Ti, then we don't have to do anything. That's actually something that is important here, that terminals can arrive repeatedly, because we're actually drawing here without or with replacement. So only if V is not equal to Ti, then we'll simply add the edge Ti, V to our set S. So this algorithm is actually nothing but the greedy algorithm, except for the fact that we have this initialization here, where for the greedy algorithm we just initialized S to be the empty set. Now we're doing something a little different. We draw these T1 prime through Tk prime from our known distributions, and now we connect all of these to each other and to the root. And what we hope that this brings about is that now here in this second step things get cheaper, because here we can also connect to T1 prime through Tk prime, and not only to R, T1, T2 up to Ti minus 1. And why should this be any better? Well, the hope is that here in this first stage where we're initializing, we're not spending too much, because here we're just computing once an optimal, or we're approximating only once an optimal solution. And this will actually turn out to be true, because we'll be able to show the following. We'll be able to show that the expected cost that our algorithm incurs is at most 4 times the expected cost that an optimal offline solution has. What's the expectation taken over here? This is on the one hand, of course, that these terminals arrive randomly, so they are drawn from probability distributions, and on the other hand we also have a randomized algorithm, because we draw these T1 prime through Tk prime also from probability distributions. So even for a fixed sequence of T1 through Tk, this is still random what this algorithm is doing. So what we're seeing here is that this guarantee is somehow similar to what we're getting in competitive analysis. There, of course, this offline optimum is not a random variable, because we get a guarantee for every sequence. Here, we now assume that we know these probability distributions beforehand, and the input is actually also random. And this is why this sequence sigma, this is now drawn from the probability distribution, and this is why we have an expectation here. You could, in principle, also, instead of comparing expectations, taking the expectation of the cost of the algorithm and the cost of the optimal offline solution. This is something that people have also done, but this kind of a comparison is actually much easier, which is why we're doing this today. Cool, so let's prove this theorem. How do we prove this theorem? Well, what we'll bound is, on the one hand, the cost of the minimum spanning tree on T prime that we're starting with, and then on the other hand, we'll bound the cost of the edges that we're adding to our set S later on. So the first thing that I'd like to observe is that what is the expected cost of this minimum spanning tree on T prime? Well, this has to be exactly equal to the cost of the minimum spanning tree on T, and so this will be at most 2 times the expected cost of an optimal Steiner tree on T. And why does this hold? Well, here we need that the terminals Ti and Ti prime are identically distributed because we're drawing them from the same distributions. And just to be sure, this here, the cost of the optimal Steiner tree on T, this is of course nothing but the cost of an optimal offline solution. And what we'll now do in the remainder is the following. We now let EI be the edge used to connect Ti, and we will now show that the expected sum of the weights of the EI is at most the expectation of the weight of a minimum spanning tree on T prime. And then, what does this mean? We can actually use this thing here twice, because the overall cost that our algorithm incurs, this is nothing but we start from this minimum spanning tree on T prime, and then we'll take these edges EI to connect the remaining terminals, and now just by linearity of expectation, this will be at most 4 times the expected weight of a Steiner tree on T, which is nothing but 4 times the expected cost of an optimal offline solution. So what you see is that actually the only thing that we'll have to show is this part, namely that the sum of the edge weights that we use to connect the terminals when the real terminals arrive, that this is bounded by the weight of a spanning tree, of a minimum spanning tree on T prime. And how do we do that? Let's write the following. For terminal Ti, we now let d of t minus I prime, comma Ti be the following. take the minimum of all v which are in a set t minus I prime, and now take the weight of the edge from v to ti. And what do I mean by t minus I prime? By t minus I prime, I mean all tj prime for j not being equal to I or r. So here we ask, what is the closest of all t1 prime through tk prime or r not counting ti? Let me maybe write this down. So this here is the distance to the closest of t1 through ti minus 1, t prime, ti plus 1 prime through tk prime, and we're taking the distance from ti. Now what we clearly have is that the weight of the edge that we're choosing to connect terminal ti, this will be at most d of t minus I prime comma ti. Why this? Well, here for this definition we're just restricting ourselves to only use some vertices that we connect ourselves to, and we may use for this EI, we may actually use all of these vertices and also some others. Namely, we're allowed to also use ti prime, which is not appearing in this sequence for a good reason, and we are also allowed to use the terminals that arrived so far, namely t1, t2, and so on up to ti minus 1. So all we have to bound is the expectation of the sum of these d of t minus I prime comma ti. And how do we do that? Let's talk about one of them. Now it is crucial that in this definition ti prime does not show up. And ti prime and ti are identically distributed. So we might as well write here instead, this is the expected distance from t minus I prime to ti prime. This is just coming from the fact that ti and ti prime are identically distributed, and they are both independent of t minus I prime. Cool. And now this is actually something interesting here, because what we're getting now is we could write a prime here instead, and now we'll have the distance between ti prime and the closest of these others. And we're now summing this up for all ti prime. And for this, we can now prove the following lemma. Let's get rid of all this notation with the t primes, and this is just some statement about Steiner trees or spanning trees and distances. I now take L vertices, and now these are now called U1 through UL. And now I have U minus I as the set of Uj of all Uj which are not equal to I and R. And as before, we now call D of U minus I, comma I, Ui, the minimum of all the distances that we have, or all the edge weights between some vertex V and Ui. Then the following holds. Take the sum of all U minus I, comma Ui. This will be at most the weight of a minimum spanning tree on U1 through UL. I hope now you see, okay, this is exactly the kind of a quantity that we want to bound here, but we'll see this later, how this now actually works out. Let's first just prove this lemma. So we have these L not necessarily distinct vertices, and we have the set U minus I, and we're now asking how expensive is it to connect each of these Ui to the U1 through UL, but not to UI, of course, to one of the other U's. And we say that the sum of all these will be no more than the weight of a minimum spanning tree, considering U1 through UL and also the root. What we'll do is the following. Let's consider this minimum spanning tree on U1 through UL as a tree rooted at R. So this might look like this. We have here R, and now we have some minimum spanning tree. Don't know what this looks like, maybe something like this. And now we direct every edge towards the root, so we have this minimum spanning tree here rooted at R. And now we'll now say If ui is in u minus I, how is this even possible? Didn't we say u minus I does not include ui? Isn't this strange? Well, we are not saying that these have to be distinct, so this is why this is possible. We'll define now vi as ui, and if ui is not equal to u minus I, then we'll define vi as the ancestor of ui in this tree. So what does this look like? Well, let's now see, where do we have our u's here? Maybe these might be our u's, but maybe now here actually this is appearing twice in our sequence. So let me try to visualize this by now drawing here 2 points that say those are actually appearing twice as u. So here now we our L would be 1, 2, 3, 4, 5, 6, 7, 8. And for these two, or for these two pairs of vertices, they always have that a copy or a twin of this vertex is also in u minus I. For these others, this is not true. And so what will be the respective vi? Well, this will be something like this. We'll have here this, and this as the respective ancestors. And what you now observe is that each ui vi of course corresponds to an edge in this minimum spanning tree. But each edge of this minimum spanning tree appears at most once. So this means that if we now take the sum of the weights of the ui vi, this will be at most the weight of the minimum spanning tree. I should have said maybe that here we're saying that this is 0 if ui is equal to vi. And what else do we have? The lemma now follows because, of course, the distance between u minus I and ui, this cannot be more than whatever we now chose as the connection cost. So this lemma is actually just a very simple but helpful statement regarding spanning trees, and that actually now these distances that we can use to connect vertices to each other Well, that these distances are certainly bounded by the cost of a minimum spanning tree. So this is the one picture that you should keep in mind. Again, what makes this a little less intuitive is that vertices may show up multiple times here as U1 through UL. Otherwise, this would be exactly the minimum spanning tree that we're getting here. So now we're getting something that is at most the cost of a minimum spanning tree because, for example, these two, they may connect to each other because here in U minus I, we were not saying that Ui should be not identical to Uj, but we were only saying that the indices have to be different, so actually it might happen that Ui is in U minus I. And then this will just fortunately easily work out. Good. So why do we care about this lemma? This lemma now helps us to bound this quantity here. Here we now see, okay, these distances we can upper bound or we can identically write with a Ti prime instead. And then we just apply this lemma, and then we get here the minimum spanning tree of T1 prime through Tk prime. So let's just write this down. The expected sum of the weights of the edges EI we can upper bound by the expected distances of Ti to T minus I prime. And this is now crucially the same as, well, let me do the step in between here. Take the sum of all I and now replace Ti by Ti prime. Now let's move this sum back together into just one expectation. And now on this, we can apply our lemma, which will give us that this will be at most the weight of a minimum spanning tree on T1 prime through Tk prime. And this concludes the proof of the theorem. Good, so this concludes the proof of our theorem. What turned out to be crucial here? It turned out to be crucial that, well, what we're doing in this first stage, that we're just sampling from the distributions and just connecting everything, this is something we can afford. We're losing, certainly, we already have to pay a constant times the expected cost of the optimal offline solution, but that's something that we're willing to pay because this now makes it much cheaper to connect the terminals in the second stage. I'm not saying stage, although this is not a two-stage optimization. Two-stage optimization we'll talk about very soon. But here it is just when the actual terminals now arrive, it is somehow true that, well, we've planned for kind of these terminals. If these distributions were point distributions, point masses, that, well, we'll always choose, or that we get deterministically one vertex in every step, then we would have no cost whatsoever in the second stage, when the actual terminals arrive, because we are prepared for everything. Now things are a little different, but somehow the way you can think about this is for every situation which may look like this, when this is the terminal TI, which we'll actually have to take care of in our sequence, there is also the situation in which this exact terminal arrives as a TI prime, so then we are taking care of this and vice versa. So overall, this somehow is the idea, or at least my intuition, why this is true. At the same time, it is difficult for me to really express why I think this works out, except for the fact that, well, we just have this rehearsal stage in which we just try to prepare ourselves, and somehow for this precise problem, it turns out that this is a good preparation for whatever may come. There might be other problems for which this is total nonsense, sure, but here it turns out to be a good idea to just do this rehearsal, be prepared, and then somehow the actual cost that you'll incur when the actual terminals arrive, this is now much smaller. Cool. So here in this case we get something like, although we're doing that competitive analysis, it's something like 4 competitive. Now in the second part of the lecture, I'd like to turn to the case of a random arrival order. For this, we've seen in the case of optimal stopping that also we could go down to a constant factor, which is also something like a constant competitive ratio. But for this problem, for the Steiner tree problem, we'll see that this is actually not possible. We'll see that here actually you cannot do better than what you, or much better than what you can do here we'll see that if the input arrives in random order, then you cannot do much better than what you can do when you don't know anything in advance and the input arrives in just some arbitrary order. Let's now turn to the question of a random arrival order. What can we guarantee there, or what can't we guarantee there? Well, what we can certainly do is we can certainly just run our greedy algorithm, because our greedy algorithm works for any sequence. So certainly the guarantee that we obtained there, this O of log k competitive ratio, this is also true if the input arrives in random order. But can't we do better? Now we've seen that if we know the probability distribution beforehand, we can get this down to a constant. Is this also possible if the input arrives in random order? Unfortunately, it is not possible. Namely, what we can show is the following. We will show that there is no algorithm which guarantees that the expected cost that we incur on a sequence is at most alpha times the cost of the offline optimum for alpha being in little o of log k, even when the sequence is presented in random order, and the algorithm is randomized. So this statement is stronger than what we derived for the online Steiner tree problem so far as a lower bound in two ways. On the one hand, this is now also a lower bound in terms of the arrival order. The arrival order may now even be random. Even then, we cannot do better than log k asymptotically. And also the algorithm may now be randomized. So far, our statement was about deterministic algorithms. Now here it will turn out that we can even do this for randomized algorithms. This argument that we're doing now is actually pretty robust also against randomized algorithms. And so the point is, well, even then you cannot do better than log k as the competitive ratio. How will this proof work? Well, it will more or less use the same arguments that we had for the deterministic algorithm, showing that there was no little o of log k competitive algorithm, for no deterministic little o of log k competitive algorithm for online Steiner tree. So what we'll again be using are the diamond graphs. So this is what we'll write as dj. This will be the diamond graph of level j. So what does d1 look like? d1 is nothing but this graph. d2 is now looking again the same way, but one way you can think about this is you replace each edge in this graph again by this graph. So you'll now have here this graph sitting in between and also at the bottom. Or if you now like, you can also try to draw the diamond graph for level 3. Then we'll again have these left, right, top, and bottom vertex. Then we have again a diamond graph of level 2. Then we'll have the diamond graph of level 1. We'll have 4 of them. And probably then you'll realize, okay, this is actually very annoying to draw. But this is generally what it will look like. So again, here, this part, and also in this part will each have a diamond graph of level 2. Or more generally, we'll have dj plus 1 looking like the following. We have our 4 big vertices, and now they are connected by the dj graphs. Cool. So what will this now look like? Maybe let me go back to the D2 or D1. What was the problem in all these graphs? Well, let's suppose this is the first terminal, and then we choose either the top path or the bottom path, where this is now the root. And it may not happen that this is the second terminal or this is the second terminal. And then the optimal offline solution will just be one path, whereas the solution that our algorithm computes will usually be, or sometimes at least be, one path plus an additional edge. And the same thing can happen here also in D2. We have here, this might be our root, and this might be our first terminal, and then we choose one path. Maybe let's choose the all top path. And then maybe this is the second terminal, or this is the second terminal. And suppose we now took the top path, and this is the second terminal, then we have to use one of the other paths. So this, or this. Let's say we choose this path here, but if now this and this are the third and the fourth terminal, then we again have to pay connection costs to them. Although, as it turns out, let's say these, and these are our terminals, then they actually just lie on a single path. So our idea for now to construct such a bad example now is actually to draw one of the paths from left to right uniformly at random, something like this maybe, and we'll then have each vertex multiple times in the sequence so that the order looks very much like a random order. And then the idea is, because this is a random path, we don't actually know in advance while this vertex arrives, we don't know whether this or this was is the actual path that it is lying on. So if we have this, and this vertex, the path still may be this path, or it might be this path, or it might be this path, or it might be that path. Let's try to formalize this. Before we get there, let's introduce some notation, namely here in dj I call these two vertices of level j. So here we have dj plus 1. dj plus 1 consists of two vertices of level j, which are, one of them is the top one of them is the bottom one, and both of them connect to diamond graphs of level j. And maybe there is another level, then this will be a vertex of level j plus 1, of course, or maybe this one, depending on how they are connected. And what will we do now? We'll consider the case that k is a power of 16. And we let L be a half times log to the base of 4 of k. This, because we have a power of 16, this will still be an integer. This is why we are assuming only this case here. And now what we'll do is we'll consider the diamond graph of level L. And what we'll now have to do is we'll have to define a sequence of terminals. And we'll do this as follows. We'll just draw one path from left to right in our diamond graph of level L. This one crosses through 2 to the I copies of dl minus I, and therefore also through 2 to the I vertices of level L minus I, and this is true for all I in 0 to L minus 1. And our sequence is now the following. We'll request every vertex of level L minus I in the path 4 to the L minus I times. What's the length of the sequence? It is now take the sum of all 2 to the I times 4 to the L minus I. Why this? This is the number of vertices that we have times the number of copies, or the number of how often do we request this vertex. And this is now the length of the sequence, and we'll now see that, okay, how big is our sequence now? The length of the sequence will be at most 2 times 4 to the L, which is exactly k. So this is why this is still a feasible sequence, although we request actually every vertex pretty often. What's the point of this? Maybe let me go back to our examples here. Maybe let's go back just to this D2. We now have vertices of level 2. So this and this are vertices of level 2, and we'll have some other vertices of level 1. Now what we'll do is we'll draw one path uniformly at random from the left to the right. Maybe it's this one. And what else did we now do? We'll now have I being equal to 0 or to 1, because our L is 2, and now we'll have vertices of level 2 and vertices of level 1. And the vertex of level 2 we now request 16 times. The vertex of level 1 we can request only 4 times. So we're actually leaving some slack in here. One might also change this. So this top vertex here, this will be requested 16 times. This will be requested 4 times each. And what's now the point of this? The point is that most likely it will now happen that this vertex arrives before this and before that. Because here this we have this vertex 16 times in our sequence. These two we have only 4 times each, so it is, and this will also hold much more generally, it is very likely that this arrives before one of these. And this is now maybe not so very explicit now happening because because this example is tiny, but because we're connecting this to the root here, what will likely happen is that we choose the wrong of these paths, because when this vertex arrives, we have no idea whether the top or the bottom vertex will be used here. And the idea is that, okay, with probability a half, we're choosing the wrong on both sides, so we'll have to pay for a new connection. Let's write this down a little more formally. We let Vjb be the bth level j vertex viewed from the left. And we let xbj be the cost incurred by our algorithm to connect Vjb. And what we now claim is that the expectation of xjb is at least 2 to the power of j minus 3. What does this cause? This causes that the expectation of, well, we now have L different levels, and there we'll have 2 to the L minus j level j vertices, and now by linearity of expectation we can then say, okay, this is the sum of the respective expected individual cost to connect the jth level the bth level j vertex. And now the hope would be that each of them is at least 2 to the power of j minus 3. And if you now do the math, then you will see, okay, what we're getting here is that we have 2 to the power of L minus j times 2 to the power of j minus 3. And we'll have this L times, because now what we'll see is that this is L times 2 to the power of L minus 3. Or L over 8 times 2 to the L. And what's the point of this? This now means that the expected cost that the algorithm incurs on our sequence, on our random sequence, will be at least L over 8 times 2 to the L, whereas the cost of the offline optimum will always be, I can even say here, at most 2 to the L, which means that this ratio will be at least L to the 8, L over 8. And our L was in the order of log k. So all we actually have to do is to bound the cost incurred by the algorithm to connect some arbitrary level j vertex at the point when it arrives. And how do we do that? To do that, we see that this vertex arrives at a certain point with a certain probability, or what we'll do is we'll ask, how likely is it that we've not seen vertices of a smaller level in the adjacent diamond graphs at all? And if that's happening, then the expected cost will be high. So what will this look like? We want to now bound the expectation of xj, b. Okay, what does this look like? We have our vertex, which might look like this. And then we'll have left of it this diamond graph of level j, and we'll have right of it also a diamond graph of level j. All of this together is a diamond graph of level j plus 1. Now, how many copies do we have of such a vertex, or how often does it appear in our sequence? So this appears 2 to the j times in our sequence. And what do we have inside such a dj? Inside such a dj, we have 2 to the I vertices of, or 2 to the I terminals, to be precise, of level j minus I, and each is requested for to the power of j minus I times in the sequence. So, what's the probability that the level j vertex is the first among all these terminals it is 4 to the power of j divided by the overall. So because here we have 4 to the j times that it appears this in our sequence, and now we'll have 2 to the I times a vertex of level j minus 1, j minus I, which appears 4 to the power of j minus I times each. And this is now at least 1 over, take the sum of all 2 divided by 4 to the power of I, and this will be a half. So, and this is now the magic why we chose that this vertex appears so often, is requested so much more often in the sequence, because now with probability a half this arrives before anything in here and in here. And now before this arrives, we have no knowledge about it. Namely, what can happen is that it is either this vertex, or it can also be that other vertex down here, which would lead us via this other path. Let me try to draw this here. So this might be as well what might be happening. And so, with probability a half, the algorithm only chose paths via the twin vertex of level j. And so, with probability a half times a half, we need to pick an entire path through dj, and this has length 2 to the j minus 1. And so this means, or this I should say with probability at least all this is happening. There can be other things happening, but generally this is at least the probability that this is happening. So we'll have a half times 2 to the power of j minus 1. So we'll have that this is 2 to the j minus 3. And this is exactly what we were claiming. Good. So, How does this entire argument work? Well, I think this is the kind of picture that you should keep in mind. With probability a half, we are just on the wrong side. Our algorithm was just on the wrong side of the graph so far. It was choosing, and maybe this is easier to show in this picture here. So maybe there is something, this is part of something bigger. Then, before this vertex is revealed, it is just equally likely, or this vertex is equally likely to be this one vertex. So the algorithm doesn't actually know whether this or this will be the vertex before, and we're now at a point where none of this ever showed up so far. So before this, now either the algorithm chose this path, if any. Maybe the algorithm didn't choose anything inside this D2. Okay, then nothing's happening. Otherwise, it will maybe have chosen this path. Then we'll have to now pay this connection, or it has chosen maybe this path, but then it is equally likely that everything that we have up here is actually happening down here. And then also, with probability a half, we now have to pay the new connection. And so this is what is happening here. With just constant probability, things go wrong. And the crucial thing that you should keep in mind is that the random order doesn't make things much easier here, because we can just request one terminal very, very often in this sequence. This doesn't actually change the cost of the optimal offline solution, because once a terminal is requested, nothing changes. It is, once it is connected, we don't have to connect it again. But this now turns the actually very nice random order suddenly into a bad order, which is maybe not bad overall, but which locally is always bad enough. Good. So, what have we seen? We've seen that known probability distributions allow us to be something like constant competitive, but but this random order, this does not help us. There we can still only be log k competitive, or constant times log k competitive. Now I'd like to give you a bigger picture of what kind of what other probabilistic models for online problems there are out there. Let's now wrap up our discussion of probabilistic online models. We've seen the case where we had known probability distributions, and we've seen the case that we had a random order. And sometimes they are similar, sometimes they are different, but generally they are incomparable. So it's not that somehow here things are definitely easier or harder than they are here. Certainly, whatever you can achieve if everything is worst case, you can certainly also achieve when you know distributions or when the order is random. Sometimes in these cases you can actually do something better than this. This is what I'm trying to indicate by these arrows. Now, what are certain other models? Well, there's, for example, also the model where you have unknown but identical distributions. And this is actually easier than if the input arrives in random order. Because if the input is drawn from identical distributions, then automatically it will appear in a random order, but it will have still a little more structure than here in this random order. Here this is somehow like drawing with replacement. Here this is like drawing without replacement. Drawing with replacement is easier because intuitively this is maybe clear that it is somehow more likely that you will see something again that you've already seen before. And what is the easiest of these, which unifies all of them? This is that the input is drawn from known identical distributions. So in advance, you know for every step, the input will be drawn from exactly this distribution. They are independent, all what that we're assuming here is always independence between time steps, and also that here we know in advance which probability distribution is being applied. Now then you can say, okay, we may have different distributions for every step, or we may say that we have that we don't know the distribution beforehand, but it is still the same. There's also the question, what happens if the distribution is different in every step and we don't know anything about it in advance? Well, this is exactly this model, or a variant of the worst case model, because if the distribution is different in every step and we don't know anything in advance about it, then we just cannot learn anything about it. So effectively, every online problem you can study in such models. There are even more than these models, but you can always ask, what could you do if you knew probability distributions? What can you do if you know that there are at least probability distributions? And then you can always ask, what will be your how good can you do compared to the expected offline optimum solution? Or maybe also, how good can you compare to the best online algorithm, which would be the optimal policy of the respective Markov decision process. Good. So this is it for today. Thank you very much for your attention. Please do reach out to me if you have any questions, and I hope to see you next time. Stay safe. Bye.